Good morning, everyone. Today I'm gonna talk more about simple harmonic motion. And yeah, so I said last time, simple harmonic motion can be circular motion or spring motions, right? So this time I will show you how simple harmonic motion changes as a function of time or period, right? So let's assume we have a spring here, right? And then you see there are two t's actually, right? So you see here small t and large t, right? And then large t is what? Large t is a period, and then t is actually the real time clock. Okay, so make sure you see the differences between those two. And then of course when t equals 0, what happened? The ball or the mass attached to spring is in equilibrium condition, right? And then you have a, one force of T, the object is moving downwards. So it moves about half of its amplitude, which is A, right? And then sometime later, you have it reaches to what? The maximum displacement, and then moves up and come back to its equilibrium condition, the original position, right? So then now we'll observe three parts: position, velocity, and acceleration, right? The position is very simple, right? When t equals 0, it has a maximum position, A, right? Amplitude, right? So in other words, it's a stretch the maximum amount, right? It's actually compress it, right? This much, which is A, right? So let me see, yeah, right? So here, right? This is your equilibrium position, and this is this distance is your amplitude A, right? So then the position, so I'm talking about the position, right? And then sometime later, its position is now 0, which is origin here. And then sometime later, actually half a period later, it goes minus A, and then moves up, coming back to origin, and then positive A. And then repeat this, cycle, right, over and over. So basically, you see the maximum value of a position is A, and the minimum value is minus A, right? It's clear, right? So the mass, so let's read it carefully. The mass starts at this maximum positive displacement, which is y equal A, and the velocity, so I'll talk about velocity later, right? So then now let's talk about velocity here. So this position, when t equal 0, what is that? You compress your spring all the way up here, right? And then this is just before you release it when t equals 0, right? So then what happened after you release it? So that time, your velocity here is of course, 0, right? Because the spring is simply attached to the mass is attached to the spring, right? So your velocity here is basically 0. Oops, right? And then sometime later, what happened? The object is moving downwards, right? So if assuming upward is positive, downward is negative, your velocity is now downward, so it's a negative, right? So it's moving negative. And then when does the spring has maximum velocity? When it's at the midpoint, right? Equilibrium position, right? Here, right? And then, so that's why your velocity has a minus maximum value because it moves downwards. And then when it's fully stretched, right here, when the period t is 1/2, the velocity is 0, right? Because when the spring is all the way stretched, it's a temporary stops, right? And then spring moves backwards, in other words, moving upwards, right? And then now speeding up. and then it's at the midpoint here, the velocity of the spring is now maximum. And then when it's come back to its original location where you have a full compression, the velocity come back to zero, right? So in other words, imagine, position is all the way. You compress or stretch your spring. For this case, you compress your spring, right, by amount of A amplitude. Of course, velocity is zero. Once you release it, position passes through origin and come back to maximum stretching, right? The velocity start increase and then reaches its maximum velocity and come back to zero velocity, especially when the object is the spring is stretched all the way, right? Good. And then the third thing is acceleration. It's a little bit more complicated, but let me go over this part again. The velocity is zero, right? Of course here. But the acceleration is negative because there is a net downward force. So assuming the force here, of course here, is what? The net force is acting downwards. So acceleration is actually negative here, right? Because Newton's second law, F equal ma, right? So if F is a negative, then A is a negative as well, right? So the acceleration here is maximum minus, and then start increase, and then reaches its maximum acceleration, and then come back to its actual in the minimum value again. So you see, you have all these three graphs are sine or cosine waves, right? So that's important. So later I will introduce how you describe these three motions in terms of a sine or cosine function. And then I think they explain the same thing. You can read this slide, but I highly again recommend to go back to your textbook and then read the textbook, this section very, very carefully. Okay. And then same thing happened. So now we start with the position graph. The position versus time graph for simple harmonic motion is cosine curve, or sometimes we can use a sine curve as well. But for this course in general, we will use this cosine function. And again, because this second part is a cosine function, right? And then this is basically amplitude time cosine function. And as you might know, again, cosine or sine function, maximum value plus minus 1, right? So the position maximum value is A when the cosine value is 1, right? And then my minimum value of x is minus A when the cosine value is negative 1, right? Okay. So again, x indicate the position as a function of a time. And then cosine function also can be written in terms of a frequency. Why? Remember last time, what we did last time, right? So we talk about frequency, the relationship between frequency and period is what? 1 over t, right? So if you simply rewrite this equation, so replace 1 over t with the frequency, right? So these two equations are equivalent, right? And then the velocity graph is up-down function, upside the down sine function with the same period, the t, you see here, right? Upside down sine function, right? With the period t. So you have a Vmax times the sine 2 pi ft. Okay, so again, even though so far we don't know what is a Vmax value, because you see here, this is a Vmax value, but we haven't specified this value actually so far. Okay, even though position value has a maximum A, minimum minus A, we haven't specified Vmax and the Amax yet. That's what we will talk about later. But remember anyway, here, your Vmax of velocity function is minus and sine function. Okay, so even though this course is not, calculus based, course, the easiest way to remember this one is, I think you guys already, some of you already learned, calculus. So xt is a cosine function, right? So velocity that you learn, I believe the physics one, what is a vt? Vt is actually delta x over delta t. So in other words, this is a dx over dt, which is a derivative of a x function. So if you take the derivative of a cosine function, what is that? It's a minus sign. So that's why you have a minus sign here. And then if you take one more derivative of sine function, that's again come back to cosine, right? With the same sign minus, right? So that's the easier way, right? So even if you're not, familiar with the, the derivative of a cosine or sine function, but you can simply, memorize this one because initially you have a cosine function for xt, and then sine function for vt, and again cosine function for at, except it's a coefficient v max, a max, and amplitude a, right? So again, you can either say describe your motion and position as a function of time, right? So then it can be either sine or cosine, right? So if everybody know when t equals 0, so then sine function is 0, right? And then when t equals 0, cosine 0 is 0, is non-zero, right? So if your oscillation start from origin, you choose a sine function. If your oscillation or spring starts either maximum compression or stretch, you use a cosine function, right? And then, yep, that's it. So then basically this is a x as a function of a small t. Your y-axis is a x. Your x-axis is a time, right? And then also be careful. You see this one period, one per period of this sine or cosine function, how much time you need? Period t, right? So then if you have when small t is a period t, cosine function come back to cosine 2 pi, so it come back to its original value, right? So this is why this is a periodic function. And yeah, so this is again the same explanation about the pictures below, the previous pictures. And now example, so yeah. Sustaining the motion of the glide of spring. So you have a spring here, and then you have attached a glider there, right? And then this is a position, right? So the very fundamental that you have to memorize for this chapter and the next two chapter is a basic function of position. That is again, x is a amplitude, which is a maximum value, right? And then cosine, in general, we will use cosine. And then you see here, 2 pi t over t, right? Again, times a t, right? Good. So you got so in general, I don't like to ask you to memorize something in this course in general, but sometimes you have to memorize the very core formula for each chapters. Okay, so this is a basic formula you have to memorize. Okay. So then now we can start. So basically you have a air track, glider, and the frequency is a 0.5 hertz. So that means F is a 0.5. So what does that mean? Again, last time, what did I tell you? If you know frequency, you find T immediately, right? Or you can change this formula, what? To cosine instead of a 1 over T, that's a frequency. So you can say this is a 2 pi ft as well, right? So then you are looking for first xt graph. So what is your A? A is a maximum value of amplitude. So this is a 0.5. 0.12 meter or 12 centimeters. So I'll say I'll use MKS 120.120. And then you have a cosine and then 2 pi. What is F? F is a 0.5. So 1/2 times a t. So your cosine function, the position function is simply what? 0.12 cosine, cancel, pi t. That's your x function, right? And then let's read the problem carefully again. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeter. That's why your A is 12 centimeter, right? Where will be the glide be 1 second after it is released? So that means you're looking for the position as a function of time. So the answer is very simple, right? So basically you're looking for x value when t equal 1. So your x is simply what? 0.12 times a cosine pi, right? What is a cosine pi? Everybody remember cosine pi value? -1. So that means the answer x here is a minus a 0.12 meter or 12 centimeter. You can also check the answer using this formula, or you can also check it from the graph, right? 1 second later, what is your position? 1 second later, your position is a -12, right? Good. So then let me see how they solve it. Okay, so that's fine. And the second question is, what is the velocity at this point? So what is the location here? So it's if you think about the spring, what does that looks like? So initially you stretch. So this is a without stretching or compression over your spring, right? But now you stretch your spring 12 centimeters. So now this is your 12 centimeter, and then this is a T0 position, right? So this is the when T equals 0, right? This corresponds to this position. And then once you release it, 0.5 seconds later, it come back to here. Here again, the velocity is maximum. And then 1 second later, what will happen? Which is a half period. What will happen? It will fully compressed. And then temporarily stop there, right? So then what is your velocity there? Your velocity there will be 0, right? And I said the last time, the spring motion and circular motion are basically the same. And then I'll explain why. You have a circular, and then you see here circular motion and simple harmonic motion are motions that are repeat, and the uniform circular motion projected onto the one-dimensional is a simple harmonic motion, which is a spring motion as well, right? So you have a light from projector, and then you have a turntable, and then you have a ball here, and then you follow the ball's shadow. And then what will happen? Ball shadow will move back and forth. That's exactly the same as a spring moving back and forth. So this circular motion, again, is exactly the same as a spring motion. So then now the x component of the circular motion when the particle is at angle pi. So now let's think about circular motion of the ball in this location, for this case, right? So assuming your particle is here and then angle is pi, and then what is the position which corresponds to this length? I believe you guys have a idea about how to find, if you have a right triangle, right? And then your hypotenuse is given, and then you're looking for A, B, two lines, right? You remember you use a sine or cosine, right? So then when this is adjacent, you use cosine. If it's opposite, then you use sine, right? So then your velocity here, and then your position is A cosine pi. That's exactly your sine wave, right? So the angle at the time later, pi is omega t, right? Well, think about y. So last time I introduced angular velocity, right? Omega. What was that? Angular velocity is a angle change, the theta over time, right? For this case, angle change is a pi, so it's a pi over t. So your pi is a omega t, right? So this is your angle, so you can say this is a omega t, right? Or your omega is what? 2 pi f or 2 pi over large t. That's what we did the last time, right? And then the magnitude of the velocity, maximum velocity you see is gonna be 2 pi f times a amplitude a. So you simply have a omega 2 pi f times a will be maximum velocity. And then square of 2 pi f times a will be maximum velocity of a acceleration. Okay. So then you see again, we have a position graph. And then because now you remember velocity graph with us, you change cosine to sine, right? And then acceleration graph, you come back to cosine function again, right? So the velocity graph is again, maximum velocity graph is what? As I said earlier, just said 2 pi f times a. So this is a maximum value. And then you have a minus sign, and then change the original function to sine function. And then acceleration graph, you still have a minus sign, I'm sorry. And then you have a square over 2 pi f. And then you have a original function, right? So the maximum value is again 2 pi f squared a. So then you see three important, function. And then your basic function is here. And then amplitude is the maximum value is a. And then take the derivative of what you change your velocity function from cosine to sine, and the maximum value is a 2 pi f, which is omega times a. And then acceleration, you still have the minus sign, and then you change sine to cosine, and the maximum value is a 2 pi f squared times a. So simply you start with the a times the 2 pi f, and then another 2 pi f squared, right? And then you start with the cosine, sine, cosine again, right? That's the easiest way you remember this. So then now, pose and think this question. There's a mass oscillates on a horizontal spring. Its velocity Vx and the spring exert force Fx. So it's a spring force, right? Simple harmonic motion at the time indicated by the arrow. So right here, right? And then remember, this is a position graph, right? Position graph. But basically, you don't need to remember this formula to solve it. You can, but based on your experience, I believe you can solve this one as well, right? So what happened here? You stretch your spring or compress your spring maximum, right? And you release it, right? And then what happened? Maximum velocity at the midpoint, and then all the way, compression, and the velocity is 0, and the maximum velocity, and come back to its original location, right? And then go, and then here, what happened? Your velocity is up, of course, 0, right? And the force is what? Acting to the right, right? So the answer is D, right? And then, what is that? One second. Okay. Okay, this is speed. Now, again, a block oscillates on a vertical spring this time when the block is at the lowest point. So basically, you stretch your spring all the way down. The acceleration, that point, is what? What is the actual force acting on it? The force acting on the object is the upward, right? Because it will, once you release it, the object will move upward, right? Accelerating, right? So the force or acceleration direction is a positive. Okay. And then you have a John Hancock Center in Chicago, 100 stories high, and then there's a wind, to sway the building, right? So read the question. Wind day, the top of the building oscillates with the amplitude 40 centimeter, right? So the amplitude 40 centimeter, what does that mean? Your A is a 0.4 meter, right? And then period is given. What does that mean? Because your period is T is a 7.7 second. So you basically know your frequency, which is a 1 over 7.7 as well, right? What is the maximum speed and the acceleration of the top building? So now, first, find out your position function, position equation, right? So your x is what? Amplitude 0.4 times a cosine 2 pi f, or 2 pi divided by period times the t. That's your original function, right? And then you're looking for maximum speed. So maximum speed, Vmax, what is your Vmax? 2 pi f or 2 pi 1 over t omega, which is this one, right? So 2 pi 7.7 times what? Amplitude 0.4. That's your Vmax. And your Amax is what? Basically the same as a Vmax, except what? 2 pi over 7.7 square times a 0.4. That's it, right? So you can either find the frequency, but basically you don't need the frequency, right? Because you can use 1 over t directly, right? So this is a 2 pi f, 2 pi, right? Instead of a frequency, you can still use a 1 over t times a. That's your maximum v. And then a acceleration, simply square times a, right? Again, always use a MKS, this course. And then another example, which is not in your textbook, I believe. I take this one, another textbook, but basically will help. So a classic, children's toy consists of a wooden animal suspended from a spring against springs in primary motion, right? If you lift the toy up by 10 centimeter, so that means your amplitude here is a 0.1 meter. Again, you always have to use the MKS, right? And then gently bob up and down, completing 4 cycles in 10 seconds. So what is the frequency? So now, definition of frequency, what is that? How many cycles you complete in 1 second, right? So basically you complete 4 cycles in 10 seconds. So your frequency is up 0.4. Every second you complete 0.4 cycle. So basically then, if you have a F, so your T is a, right? What does the toy first reach its maximum speed, right? When does the toy first reach its maximum speed? And then what is a speed actually? So we can find its maximum speed first. And then in order to find this maximum speed, you find xt first. Again, amplitude is what? 0.1. Then you have a cosine 2 pi t, which is a 0.4 times t. This is your original position spring function. And then your Vmax is what? This quantity, omega, times a amplitude, right? So this is your Vmax, right? So that's actually when does the toy first reaches maximum speed, right? So this is the one. And then once you have this value, and then what is your V value, right? So let me use this one, right? So your frequency is 1 over t, so 0.4 hertz, you can find it, right? And then B, your Vmax is a 0.25, as I said, the 2 pi f or 1 over t times a 0.1. That's your Vmax. And the third one, what are the position of the, so 1 second. right? So we have to find the t, right? The time, right? The figure 14.51, where's the figure? Yes, so here figure shows that, you know, t over 4, right? That's a quarter of a period, right? Shows that the toy first passes through the equilibrium position, right? So what does when the toy first reaches maximum speed? So then let's go back to this graph, right? This is a position when the toy reaches its maximum velocity, right here, right? Does it make sense? Because again, your velocity here is basically 0, and your velocity here is a maximum, right? So you're assuming again you have a spring, right? And then this is the original equilibrium position, but now you stretch your spring all the way this much, right? And then this distance is again amplitude, right? And then once you release your spring from here, your velocity here is actually 0, right? And then when do you have a first maximum velocity? When it passes through the midpoint, right? So it increases velocity and then slowing down and stop here, right? So first maximum velocity, and then when it come back, second maximum velocity. So then how long will it take? Quarter period, another quarter period, another quarter period, another quarter, right? Basically, so when does the toy first reaches maximum velocity? That's actually t over 4, right? Because we already find the t, right? And we know t is a 2.5 second. So the answer is a quarter of it. And then see what are the position and velocity 4 seconds after you release the toy, right? So 4 seconds is roughly here. And then you cannot, find the exact position here. That's not easy, right? Because basically you're looking for this height here, right? That's not easy, but you can use the original formula, right? Our position x, this time we use the y, but because it's a vertical motion, but basically this is the same as a x, your position. So we have a times a cosine 2 phi f t. So we know a, we know f, and then this is when t equals 4, the value you have here is gonna be position. So you see it's about 0.1.08, which is very close to the minimum position, but slightly after that. It makes sense, right? And then you can also find your velocity, because your velocity function is what? Minus Vmax, and then you change the sign function, right? So your minus Vmax, we already find it, 0.25, right? So this is a minus 0.25, and then you have a sine function, 2 pi f and 4. So the only thing is everything is a known value except this time here, right? So just insert 4 here. And then if the question is what is the position of what is the velocity, 3 seconds after, then you simply insert the 3 here, find the value for v. That should be your answer. Right? And then 500 blah gram. So again, whenever you see, unit which is not MKS, change it immediately. This is a 0.5 kilogram. Block is attached to a spring on a frictionless horizontal surface. The block is pulled to stretch to the spring by 10 centimeters. So this is A is your 0.1 meter, right? Then gently release. Short time later, as the block passes through the equilibrium position. That means the center position again. So this position, the center. So then its speed is 1 meter per second. So that what is this value? This is a V max, right? So what is the block's period, right? So we can find the period how? Because we know how what is a V max? 2 pi f times a, right? So that's a V max, right? So basically we know 2 pi, and then we don't know what is the frequency, but we know a is a 0.1, and that is a 1, right? The V max is V max is 1. So then we can find the frequency. And once we know frequency, you can change it to period, or you can immediately find V max is what? 2 pi over TA is a 1. So again, you solve this one for t, you find the period, right? So then, yeah, 2 pi f is 10. So then 2 pi f is 10. So this is 10 times 0.1 is 1. That makes sense, right? And then we can find the t is a 0.6 t 30 seconds. And then what is the block speed at the point where the spring is compressed by 5 centimeter? So then when x is a 5 centimeter, that is 1/2 of the amplitude, right? So we have a 10 here, right? So the cosine omega t is 0.5. What does that mean here? What is our original x position? X is what? Amplitude 10. So this is a 0.1 times a cosine 2 pi f, right? Which is omega, which is a 10, right? This is 2 pi f times a t. This is our original function, right? So then, so the question is when the block is when the spring is compressed by 5 centimeters. So that means that this is what? 0.05, right? So then you see if you cancel this one by 10, multiply 10 both sides, you see cosine 10t is a 0.5, right? So then how you find the t here? You have to use a inverse cosine function to find the t. Then you see you can find the t value here, and then if you insert t value to the v equation, right? Then you will find the velocity of it. I highly recommend you to complete A and B by yourself. Okay, see if you can get the right number, right answers. Okay, again, if you're not sure, please let me know. And that's it. Again, I didn't solve this question B completely. But make sure you can solve it, and if you're not sure, contact me, or you can have a discussion with your peers. Okay, so the basic idea here again for today's lecture, we have learned 3 basic equations, and then once you have these equations, right, and then where Bmax is a 2 pi f a max is a 2 pi f square a, right, and then so the variable for this equation is t, small t, right, all other things are known for the problem in general, right? So once you insert the t, you can calculate whole value, that's the position. If you insert the t for v equation, you can find the velocity at that moment, and the same for the acceleration. Okay, I will see you guys on Tuesday. Thank you.